Hey guys, today we're going to talk about acids and bases. So we're going to start with some of the things that you guys already know. So most of you by now know that acids have a low pH. In fact, their pH is always less than 7. Please do not say from 0 to 7. It is possible to have a negative pH. But acids do have pHs that are less than 7, and the lower the pH, the stronger the acid. Something else you guys know about acids is they turn litmus red. Litmus is a type of indicator paper, and it's called indicator because it changes colors in the presence of an acid. Something else that most of you know about acids is that they make hydronium ions. In the past, you've probably heard that it makes H+. Now, since you are in high school, you need to know that H+ doesn't really exist. Instead, that H+ joins with the water to make H3O+, and we call that hydronium. And the H in pH actually is hydronium. And we're going to talk in our next lesson about how we figure out the pH mathematically, just by knowing the concentration of our acid. Okay. Some other things that you probably know about acids is that they taste sour. They can itch or burn if you spill them on you. And they usually have strong odors. There are some common strong acids that you should be aware of. The main ones that we work with are hydrochloric acid, nitric acid, and sulfuric acid. You should all be able to recognize those three as strong acids and assume that any other acid, especially the organic acids, are weak acids. You also already know a lot about bases, so let's talk about some of those properties. Bases have a pH that is greater than 7. And again, you have probably heard in the past that the pH goes from 7 to 14. That's not actually true. pH can be much higher than 14, but it is always greater than 7 if it's a base, and a pH of 7 is considered neutral. Bases also have some properties that you are familiar with. They turn litmus paper blue. They generally give off hydroxide ions. And some things about touching them, bases make your skin feel slippery. They taste bitter. Not that we're going to eat any of them in here. And some strong bases are anytime you have an alkali metal with hydroxide. So sodium hydroxide, potassium hydroxide. Those are examples of strong bases. Today we're going to talk about 3 different definitions of acids and bases and what they mean. The first and simplest is the one you've seen before, and that is the Arrhenius acids and bases. By the Arrhenius definition, acids dissolve in water to make hydronium. And bases dissolve in water to make hydroxide. Most of you guys have in the past recognized acids and bases because acids start with H and bases end with OH. And that's the Arrhenius definition. Something else that you should know from the Arrhenius definition is what we call a neutralization reaction. An acid plus a base makes a salt plus water. It's really just a double replacement reaction. In this case, since I'm using hydrochloric acid and potassium hydroxide, the salt that we're going to make is potassium chloride. Because remember, salt just means ionic. Arrhenius acids have special naming rules. So bases, we're just going to name potassium hydroxide, calcium hydroxide, just like we used to do when we were doing naming back in Unit 4. But acids have special names. There's two types of acids. We have binary acids, and we have oxyacids. You might have guessed, oxyacids are acids that have oxygen somewhere in them. So binary acids always start with hydro. Then we put the name of the anion, and then it ends in ic acid. For example, HCl is hydrochlorine, so chloric acid. Nice and simple. Oxyacids are the ones that come from polyatomic ions. So you need to know the name of the polyatomic ion in order to name the acid. Oxyacids do not start with hydro. What you're going to do is take the name of the anion and you're going to change it. So if it's an 8, like sulfate, you change the ending to "ic," sulfuric. If the polyatomic ion is an ite ion, hypochlorite, then you change it to us acid, OUS. So one of the things I'm going to ask you to do right now is I'm going to list all of the acids that have chlorine in them, and I'm going to ask you to take a second to name them. So I'm going to ask you, once you see the acids, I'm going to ask you, once you see the acids pop up, I'm going to ask you to actually pause, name the acids, and then check your answers. At this point, you should pause. Okay, hopefully the answers you got were hydrochloric acid, hypochlorous acid, chlorous acid, chloric acid, and perchloric acid. And all we did here was change the names of the polyatomic ions to the new endings. We also have a special word for things that make H3O and OH at the same time. And that would be water. Because it makes both hydronium and hydroxide, we call it amphoteric. And all of that is the Arrhenius, or simple type of acids. But over time, we realized there were a lot of things that acted like acids. They tasted sour, they itched and burned, but they didn't fit that definition. So two scientists working separately came up with a new definition. Those scientists were Bronsted and Lowry. Bronsted and Lowry said everything had to do with protons. So they define acids as proton donors. And bases are proton acceptors. And something that they added in is that every acid has a conjugate base, and every base has a conjugate acid. Because an acid, by giving up a proton, turns into a base, something that can take in a proton. So an example would be dissolving ammonia in water. What happens in this case is that one of the hydrogens from water, hydrogen being a proton, moves over to the ammonia. Now we could guess that ammonia was a base already because it makes a which? Hydroxide. Okay? But it's a Bronsted-Lowry base because it can accept a proton from the hydrogen. So it goes from NH3 to NH4. The ammonia and the ammonium ion are what we call a conjugate acid-base pair. You'll always recognize them because the only difference is one hydrogen. In fact, the water and the hydroxide are also a conjugate pair because water has two H's and hydroxide has just one H. And other than that, they're exactly the same. It is only the Bronsted-Lowry definition that we're going to ask you about conjugate pairs, but you should be able to recognize them, and you should be able to label things as being an acid, a base, a conjugate acid, or a conjugate base. So in this example, ammonia, which is going to accept an proton, is the base. Its conjugate partner is called a conjugate acid. It's really only an acid because it accepted the proton from ammonia, so it can then give that proton back away. Also in this example, water is going to give away or donate a proton, so it is the acid, and it makes a conjugate base, hydroxide. The last of the definitions is Lewis. You guys remember when we did the Lewis structures, the electron dot diagrams? Same guy. In fact, they were invented because Lewis realized that even things that Bronsted-Lowry didn't say were acids and bases can sometimes behave like acids and bases. So the Lewis definition switches from protons to electrons. That's why we have electron dot diagrams. So while acids are proton donors, by the Lewis definition, they are electron acceptors. What that means is that if there's a space where you can add an electron in the Lewis structure, then it's going to act like an acid. Okay. Bases are electron donors. And the way we check this is by drawing a Lewis diagram. So we're going to take as an example BF3. You may remember from when we were doing our electron dot diagrams that boron is an electron deficient element, which means that it's not going to get up to 8 valence electrons. you should do the work to double check my structure. But I am going to check my structure right now. That's my 8 valence electrons. BF3 has a space right here where there's room to accept electrons. So boron trifluoride is a Lewis acid. And it can react with a Lewis base, something that has extra electrons floating around. What's a good example of a Lewis base? How about chlorine? If we do the chloride ion, right? Chlorine has 7 valence electrons. It gets one more to have a -1 charge. The chloride ion has an electron pair that can be donated. And that makes chloride a Lewis base. Under the Lewis definition, everything can be classified as being either an acid or a base. The good news is that they all fit together. Lewis is everything. Bronsted-Lowry has some things excluded, and a radius is the narrowest definition. So we can actually do that as a flowchart. Or a Venn diagram, it's even better. So we have Arrhenius. If Arrhenius says it's a base, so do Bronsted and Lowry. And if Bronsted and Lowry say it's a base, so does Lewis. It's just that Lewis includes things that Bronsted and Lowry don't. And we can draw the same diagram for acids. There's a couple of things that you do need to watch out for. We already used the word amphoteric. There is also the vocabulary word amphiprotic, which means it can both gain or lose protons. Another way of saying that is it could be a conjugate acid or a conjugate base. And I'm going to show you an example of that on the next slide. Okay? And then we also want to be careful about the word neutral. Neutral means it has a pH of 7. Many salts are neutral. But under the Lewis definition, that explains why some salts, like iron 3 chloride, are actually slightly acidic and do change the pH of things. But neutral for our purposes means a pH of 7. On our next video, we're going to talk about the equilibrium for water and the map that goes with pH and also with titrations and neutralization reactions. But I do want to show you one quick example of amphiprotic. This most often happens when you have acids that have more than one hydrogen. For example, phosphoric acid. Okay, that can break down to make a +1 version that only has 2 hydrogens instead of 3 hydrogens, plus an H+. And that can break down to make HPO4. So if I asked you to label H2PO4 as an acid or a base, you have to be really careful about that. It's actually amphiprotic. If it is working with H3PO4, this way, the H2PO4 can accept a proton. And because it can accept a proton, we would call it a conjugate base. But if it's working with HPO4, it can actually donate a proton. and then it's a conjugate acid. During class, we're going to spend some time working with identifying the different types of acids